Hi everybody, good morning, evening, afternoon, whatever time it is. Hope you're all well, hope you're enjoying the last week of term. What I've got here, what this video is, I've collated a bunch of questions along the lines of your mock exam to practice. So you can see here, it's pretty much any topic that's going to come up in the mock. We got a bit of binomial, bit of differentiation, bit of sequences, and it's fairly extensive. It's actually a little bit longer than your mock is going to be, just so that I could cover a full range of content of everything that could possibly come up. So this will be available on Teams, and I'll have some solutions on Notebook, but I'll also have full video solutions to all of these questions too. That's the intention. There's some short answers at the end, and hopefully the video will be accessible fairly soon. Depends how long it takes me to actually make it. You can see the time. I mean, I've got my Christmas jammies on, so it's quite late me making this in the first place. we'll see how it goes. Also on Notebook are some general revision tips and some useful websites that you can use. So if you know that you need to practice a particular topic, then you can sort of investigate a few topic banks to just practice binomial, to just practice inverse functions, that sort of thing. So without any further ado, I'm going to go into this paper. I'm going to work through it question by question, and we'll see how it goes. Cool. Thanks, everybody. See you possibly online at some point in the week. Okay, so here's question 1. Let's have a quick read. We are expanding 1 plus 4x to the half, take away 1 over 1 plus 3x as far as the x squared term, and we're going to need to state the range of validity as well. I've written down the binomial expansion formula for quick and easy access as well. So let's jump straight into this. Because there's two things in this binomial expansion, so I've got 1 plus 4x to the power of a half. So I'll expand that first, and then I've got this here, 1 over 1 plus 3x. I'll expand those two things individually, and I suppose I'll just take one away from the other at the end. So let's go with this first one that I've highlighted in pink. We've got 1 plus 4x to the half. So I'm going to take this formula, and essentially what I'm doing is I'm replacing all of the instances of x in this formula with 4x, and I'm replacing any instant of n, so n in this case is a half, I'm replacing any instance of n with 1/2. That's the plan. Let's see how that goes. So it's going to be 1 plus nx, that's going to be a half times 4x, and then I've got n minus 1 x, and this again, this is going to be 4x squared all over 2 factorial. 2 factorial is just 2 times 1, which is 2. So I think I'll be able to get this first bit without the calculator. I'll double check the calculation on this bit. So we've got a half times by half take away 1 will be minus a half. This term will be negative, and it's going to be 4x squared. So I'll just work out the coefficient 4 squared, and I'll divide it by 2 factorial, which is just 2. And my term there is minus 2. Okay, cool. I don't need to go any further than the x squared term here. They did state that in the question. There we go. So there's my first bit. Since I've truncated it, I'm going to put a little wiggly equals This is what I've got so far. There technically is additional terms, but I haven't worked them out. Segueing into the first cut of the video, made a typo, did it wrong. So this time I've written it down right. So it's 1 over 1 plus 3x. I did a minus, which I've got here, and I've rewritten it as 1 plus 3x to the power of minus 1. So I'm going to go ahead and expand that now using the exact same technique as previous. So it's going to be 1 plus nx plus n minus 1 nearly did it again there, I've got it on my mind. Okay, cool. So let's establish what that is. I'm going to type it in on the calculator on the side just so I can check it properly. So it's going to be minus 1 it was, wasn't it? So minus 1 half. That's not half anymore. That needs to go. That needs to become minus 1. And it's a 3 that's being squared. So it's ooh, I don't need another half. Careful. There we go. Right, minus 1. Yeah, cool. Right, that matches, and it just works out as 9. Cool. Thought so. Just needed a check, you know. So this is going to be 1 take away 3x. This is going to be positive, this particular term, so it's going to be plus 9x squared. And I'll just pop a little cheeky wiggly equals just to indicate that it's not an exact match and they're approximate. Okay, cool. So now that I've expanded the two individual parts, I can take the two answers. One of them is here, one of them is now here, and I'm going to take one away from the other. So it's going to be 1 plus 4x to the power of a half, take away 1 plus 3x to the power of minus 1. I'll take the individual expansions, which were 1 plus 2x minus 2x squared. And then I'm going to take away the one that I've just worked out. So I'm putting this all in a bracket to indicate that it's all being taken away. So let's tidy this up. Change the signs of what's in the second bracket. And try and tidy this up. So the ones are going to cancel. X terms, 2x plus 3x is going to work out as 5x. And the other numbers are going to work out as minus 11x squared. So there is the statement. That is the expansion complete. And then I need to state the validity as well. Right? So the valid range, the first expansion was 1 plus 4x. There we go. So it was a 4x. So that was valid. Okay, so that is valid between minus a quarter and plus a quarter. If I mark that on this number line here, it's valid in, let's go for pink because I colored it in pink earlier, valid in that region. The other expansion I did, 1 minus 3x to the power of minus 1, that is valid for, that's going to be between minus a third and plus a third. And if I mark that on the diagram, that's going to be just slightly outside each point there. Okay, so the range for which they're both valid at once is just here. So it's just the smaller range out of the two. That's the validity. And that's my first question out the way. Cool. Okay, here's question 2. We are being asked to find the equation of a tangent. So I'm going to need to differentiate this. I can see that there's some terms involving y, so it's an implicit differentiation question. And there is also a coordinate that I'm given as well. So roughly speaking, I'm going to differentiate. I'm then going to plug the numbers in to get the gradient, and then I'll do the equation of a straight line afterwards. So that's my process. I've made a little note on how I need to deal with y terms. You can see that here. And I've also made a note on how to deal with combined terms that involve x and y. And I can see one here, xy squared. So let's write it down first of all. X to the 5 plus xy squared plus y cubed is 17. So what I'm going to start to do is differentiate every single term. So this is going to become 5x to the 4. The next bit is going to require the product rule. So I'm just going to write that separately, and I'm going to work it out in a bit. The y cubed will differentiate to 3y squared, but because I've differentiated y, I'm going to include a dy dx. And the 17 will differentiate to 0. So I've just differentiated each individual term there. Let's deal with the product rule part separately. So this is xy squared. In other words, x times by y squared. That's one part of the product, and then this is the other part of the product here. So let's set it up. So product rule states one term is called u, one term is called v. Differentiating them both individually. Differentiating x works out as 1. Differentiating y squared differentiates as 2y dy dx. Product rule says I should multiply like so. U times dv, v times du. That's going to work out as follows. X times 2y dy dx is 2xy dy dx. Plus v du is just y squared. There we go. So that is what's going in place of this pink cloud over here. 5x to the 4 plus 2xy dy dx plus y squared plus 3y squared dy dx. All right, lovely. Now, you can plug the numbers in at this point if you want to. I'm going to rearrange to make dy dx the subject first. So I'm going to take over any term that doesn't include dy dx. So I'm going to keep the 2xy term, and I'm going to keep the 3y squared term. The other bits, y squared is going to go over here, and so is 5x to the 4. I'll factor out this part. And then finally, I'll take this down to the right side. Okay, lovely. So I've got an expression for dy dx. I'm going to need to plug in some numbers now. So let's check what they were. It was -1, 3. So I'm going to replace all of the x's with -1s, and I'll replace all of the y's with 3's. And we'll see how that turns out. So let's type it in on the calculator. It's going to be -3 squared. Get the fraction in there ready. Make sure that goes on top. Lovely. Take away 5 lots of x to the power of 4. And then down on the bottom, we've got 2 times x times y plus 3 lots of y squared. Okay, let's see what this works out as. -2/3. All right, cool. So I've got the gradient at the coordinate. It's minus 2/3. I'm trying to find a tangent. So the tangent has that gradient minus 2/3 at the point. So the tangent will be of the form y equals mx plus c, because it's a straight line, and the gradient is just that there, minus 2/3. The other thing I know about this tangent is it passes through this coordinate, minus 1, 3. So I'll sub those numbers in, 3 over here, minus 1 there, and I'll get the c value, and I think it's going to work out as 7/3. I'll just type it in on the calculator to absolutely verify it, but I can see it already. Yes, it is. Because the entire equation of the line is minus 2/3 x plus 7/3. If you prefer, you can get rid of the fractions. You could multiply it through by 3. This isn't necessary, but you might like the look of it a bit better. It's going to be 3y minus 2x and 7. There we go. Cool. Okay, what have we got here? So this is a arithmetic sequence question. I know that because it says arithmetic sequence, that's a giveaway. And we've got what looks to be some sort of simultaneous situation just reading this. So it tells us that the third term is 4 times the sixth term. And then it says the sum of the first 20 terms is 350. Okay, so I'm going to try and formalize that a little bit. So the third term I'm going to write as T3, and it's equal to 4 times the sixth term. So if I was to times the sixth term by 4, it would work as the third term. Yeah, okay, cool. So I'm going to write in a formula for the third term. The nth term formula for arithmetic is a plus n minus 1 lots of d. So in the case of n is 3, it's going to be a plus 3 minus 1, which is 2d. Similarly, the sixth term will look like this. It's going to be a plus 5d. And I'll just tidy this expression up while we're at it and get everything over to one side. I think I'll take over what's on the left to the right so that the amounts stay positive. Sorry if you can hear the baby in the background. I can certainly hear the baby in the background. So it's 3a and 18d. Okay, so I've got some link between the a and d values. I didn't even look at what the question was asking me to do, but I can see here, yeah, find the first term and common difference. I'm going to need to use this. We've also got the sum of the first 20 terms is 350. So that is S of 20 is 350. So the sum formula is here. This is actually given in the formula booklet. So I can replace the left side with 350. N is 20. And A and D is still unknowns. N is 20 here. So it's going to be 20 minus 1. And once again, let's tidy this up. So 350 is 10, 2a plus 19d. I'll take the 10 down, divide this by 10. And I have now got a set of simultaneous equations. It's just that one there. And this one here. So I'm going to solve these together. Of course, we've got the simultaneous solver on the calculator, so we can use that as a useful check. So let's do that now, actually. So let's consider a to be x and d to be y. So it's 3x, 18, y is 0. And the other equation, oops, did not type that in, is 35. Oops, 35 is not on that side. 2x, 19y equals 35. All right, let's have a look. So apparently the values are minus 30 and 5. I will still do some workings for this. In an exam situation, you would still be expected to do this, but I know what I'm aiming for now. So let's write them down together. 3a plus 18d is 0. 2a plus 19d is 35. Let's try and get the a quantities the same. So let's times this by 2 and times that by 3. So we're going to have 6a plus 3060 is 0. And down here we're going to have 6a plus 57d, and that's going to be equal to 35 times 3, which is 105. Okay, cool. I'll take one equation away from the other. It's going to be, in this instance, equation 2 take away equation 1. So the 6a's are going to cancel. 5070 take away 3060 is 21. 57 take away 36 is 21. Yes. And 105 take away 0. Yeah, that's clearly 105. I'm hoping this works out as 5. Let's just double check. Yeah, cool. Says the d value, and let's plug it back into an original equation. D is 5. Yeah, that's going to work out just fine. There we go. Great. That's the first term worked out, and that's the common difference worked out. So I've got that first one sorted. What's this? Given that the nth term of the sequence is 125, find the value of n. Okay, so let's just put together, collate what I've learned. So I know the sequence starts on minus 30, and the common difference is 5. So the sequence is increasing by 5 each time, and 125 is somewhere in that sequence, and we're trying to work out what position it is, like what's the value of n there. So I'm going to take the term sequence, which is this. I'm going to say I know that 125 appears in this sequence, but I'm not sure what the value of n is. That's my unknown. I know everything else. So a is minus 30, and d is 5. So let's solve this. N times 5, 5n, take away 5. And should be fairly plain sailing from here. So 125 and 35 is 160. And the n is going to work out as 160 over 5, which is 32. So it should be the 32nd term of the sequence. Let's just check by plugging it back into the original formula. So a is minus 30. We've got 32 minus 1 times the difference, and 125. Good. Yep, great. I'm happy with that. Cool. Question 3 sorted. Okay, yeah, so here's question 4. It's a trig problem. We seem to have like some quadratic trig for part B. There's a counter example in part A, and we just have to show that that statement is false. Now, I've actually written down the cos 2 theta identities just because I thought these might be useful for this question. And I can see that it looks kind of similar to this identity here, but it's not the same. So I can see already that this isn't going to work. But for a counter example, all that we need to do is find one answer for which the statement is false. So for example, if you took a certain angle and plugged it in, like you could, we tend to sort of go for fairly nice angles here, like theta is 0, theta is 90 degrees, that sort of thing. Let's try 0. So you plug 0 in, And if the statement's false, we're hoping to get an unbalance. We're hoping to get something different on left and right sides here. So cos of 0 works out as 1. 2 cos squared of 0 is going to work out as, well, cos squared of 0, you can type it in, is also 1. This is going to work out as follows. And you can see the left and right hand sides do not match. So that means the statement is not true. Okay, so all you need to do for a counterexample is find one instance where it doesn't work. There might be some angles that you could plug in that it does work for. Right, so just be aware that if it states a counterexample, it says, okay, you know it's going to be false, you just have to plug in a value to just sort of demonstrate it. Part B, hopefully a fairly standard question. Let's see, so it's cot squared. Let's write it down first of all. Cot squared is 7 minus 2 cosec. Yeah, okay. And we're finding values between 0 and 360. Okay, so what I'm thinking is we're going to need to change this equation so that it's all consistently cots or cosecs. Given that we have a cot squared here, and we have an identity involving cot squared, I think we should use this. So let's jot this down. 1 plus cot squared theta is equal to cosec squared theta. Therefore, if I take the 1 over, I'm going to have cot squared is cosec squared theta minus 1. And that's what's going to go in place here. Okay, lovely. So there's a consistency now. Everything's in terms of cosec. What we can do at this point is we can call it, like, I don't know, C, just for convenience. Let's not choose C actually, because it's kind of similar to cos. Let's just call it X for now. So this is X squared take away 1, 7 take away 2X. Let's get it all on one side, and that's going to be a minus 7. And I think I can double brackets this. Let's see, the two numbers need to multiply to make minus 8 and add to make plus 2. That's going to be plus 4 in one bracket and minus 2 in the other. So this tells me that X is 2. This tells me that X is minus 4. And since X was equal to cosec, I can change this back. So cosec theta is 2, or cosec theta is minus 4. The other thing I know about cosec is it's equal to 1 over sine. Okay, so there's not a cosec button on the calculator, but there is a sine button. So if I flip both of these expressions, take the reciprocal, I'm going to end up with two statements involving sine. So it's going to be sine theta is a half. Of course, another way you can think about it is you can just take the sine theta up and take the 2 down. You're going to get the same expression there. Or sine theta equals minus a quarter. So I'm going to go ahead and I'm going to try and solve these individually. I'll sketch the sine graph for this region. So let's got to plot it properly down here. So let's do something like this. Not my best sine curve, but it'll do. And let's draw a line across at x is a half. And let's draw a line across at minus a quarter as well. And let's mark some important points. So this is 0, this is our peak supposed to be 90, it's 180, and so on. Okay. So let's solve the first one. Sine theta is half, therefore theta is inverse sine of a half. My calculator is in degrees, wonderful. Inverse sine of a half, sorry, inverse sine of a half, I've said the answer here, is 30 degrees. And by the symmetry of the sine curve, the way I get the other answer is I do 180 minus it. So it's going to be whatever the angle is and 180 minus it. I know I've gone 30 degrees across here. I can go back 30 degrees there. 180 minus 30 is going to be 150 degrees. Those are those two answers accounted for. And then this one down here now, minus a quarter. So let's take the inverse sine minus a quarter. And it's minus 14 degrees. So what that's doing is it's giving me an angle back here somewhere, minus 14. But I can still use these principles. I can say, okay, it's minus 14 point, let's call it 0.5 actually, there we go. I'm going to write that in a different color because it's not in the range. So I get the next answer by doing 180 minus that, 180, and keep in mind it's minus, so it's the double negative situation. Got 194.5, which is here. But there is another angle here which looks to be quite close to 360. Now, another way you can generate angles using the sine function, the sine repeats itself every 360 degrees. So if we had the original answer, minus 14.5, we can add 360 onto it to take us all the way across here. And let's do that. Minus 14.5 plus 360 degrees is 345.5. There we go. So our angles are 30, 150, 194.5 and 345.5. Okay, differentiation. Quite a few parts to this, quite a lot of marks available here. Lots of different rules and ideas to remember with differentiation. So let's just jump into it. I've collated quite a few ideas here. You might want to do the same. Maybe not in the exam, but in terms of revision, I think that's okay. So the first question is just differentiate these individual expressions. We've got x squared sine x, and then we've got a bunch more that we're going to see shortly. So something I'm noticing with this is it's x squared multiplied by sine x. It's two functions being multiplied together here, so I'm going to need to use the product rule for this one. So let's call u x squared and v sine x. Yep. Differentiate them individually. And the product rule says that I should get u dv plus v du, which in this instance is going to be x squared cos x, and it's going to be sine x times 2x. I'm going to write that as 2x sine x. There we go. Not too much in the way of simplifying that. I guess you could take x out as a common factor, but I don't think that particularly makes it look any simpler, so we can leave it like that. What we got next? We've got a logarithm. I should probably write dy dx here as well to indicate that I have actually differentiated it. What was it again? X squared plus 3. Okay, so If we're differentiating a log, it goes to 1 over x. I need to use the chain rule though, so what's going to happen here is I'm going to end up with 1 over what's in the argument, but I also need to multiply by the differential. If you differentiate x squared plus 3, you get 2x, and I can write that as a single fraction, 2x on the top, x squared plus 3 on the bottom. As a shortcut with logs, whatever's in the brackets on the bottom and the differential of what's in the brackets, so differentiate x squared plus 3, you get 2x, that's on top. Part 3, I believe that was a e. Yeah, e to the power of 9 take away 2x. Okay, so I've forgotten to do dy dx once again, haven't I? Let's just write that in for consistency's sake. Dy dx equals, okay, cool. This one, multiplying by differential once again, because this chain rule, e to the x stays the same. So I'm going to still have e with the same power as before. I'm going to multiply by the differential, which is minus 2, and then my result is going to be minus 2 e to the 9 take away 2x. Finally, part 4. Part 4 is a fraction. 4 divided by 3x plus 7 squared. Okay, two methods for this. Either say, oh, it's a fraction, I'll use the quotient rule. But what's maybe a bit easier is to say, okay, this is equivalent to 3x plus 7 to the power of minus 2 instead of squared on the bottom. Once we've rewritten it, we can go ahead and differentiate, once again using the chain rule. So I'm going to, in this case, this is in the form x to the power of something, so I'll take the power down. I'll take 1 off the power. What's in the bracket stays the same, and I'll multiply by the differential, which in this case is 3. So let's tidy up all these numbers out front. 4 times minus 2 times 3 is minus 8 times 3 is minus 24. And you could probably leave your answer like that. If you wanted to, you could, oops, I need to pop that minus in there. Nearly missed that. If you wanted to, you could write it back underneath if you wanted to. That's fine. Lovely. Right, what's going on here? Part B looks weird, doesn't it? Here's a function, 1 plus tan over 1 minus tan. Show that dy dx is always positive. Right. Let's see how it goes then. So it does tell us that it's dy dx. So like, clearly we're going to still need to differentiate it. Let's just verify. Was it 1 plus tan on the top? Yes, it was. So we're trying to show that dy dx is always positive somehow from this. So we're going to use the quotient rule to differentiate it, since it's a fraction. And the quotient rule says if I want to differentiate u over v, it's going to change to v du minus u dv all over v squared. That's the formula. So let's write down what u and v actually are to begin with. And du, so tan differentiates to sec squared, and minus tan differentiates to minus sec squared. Okay, so putting this into the quotient rule, I think I'm going to get a straight line to make this look half decent. So this is going to be v times du minus u times dv. Bottom of the fraction is going to be 1 take away tan squared. There we go. Right, it looks pretty gross. The top of the fraction I'm hoping will have some like cancelling out or some sort of thing like that, because the terms look very similar on top and bottom. Sorry, not top and bottom, left and right. So this is just going to stay as it is. This expands, so 1 times sec squared minus tan times sec squared. Okay, right. Lots of minuses here, so this is going to be minus 1 times minus sec squared. That's going to be plus. And I've got minus tan times minus sec squared, so it's going to be tan sec squared. Okay, so there is some cancelling. This term here and that term there are opposite signs, so they can cancel. And we're going to get the following, 2 sec squared divided by 1 minus tan x squared. Cool. And somehow now we've got to justify that that's always positive. I think the way to probably think about this is you've got a squared on the top and a squared on the bottom. You can write this as follows. It's 2 sec on the top, 1 minus tan on the bottom, but it's all being squared. And whenever you square something, whether it's negative or positive to start, you know what, once you square it, it's going to be a positive quantity. Another thing that I know about the sec function as well is that it's never 0. So just that like final bit of justification. Do I have to say, yeah, always positive? So I assume that that means greater than 0 strictly, rather than like a less than, sorry, not a less than, greater than or equal to. So this is positive, and since this top part can't be 0, the whole thing will result in a positive quantity for sure. Very neat. Okay, what we got here? We've got something arcs related by the looks of things. So let's read the question. We've got 2 points on the circle, A and B. The radius is given, R is 6. Okay, I'm just going to make a note of that. R is 6. And we don't know the angle, it's just theta. The circumference of the circle is 24 centimeters more than, right, twice the length of the arc AB. Okay, let's formulate that as well. So the circumference of the circle is 24 centimeters more than twice the arc length. So that is, it's 24 and 2 lots of the arc length together. That's what the circumference is equal to. It's 24 and the 2 arc lengths there. Okay, so the circumference of a circle is pi times the diameter. And the arc length formula is r theta. So in this case, the diameter of the circle is 6 times 2, which is 12. And the radius is 6. So let's tidy this up. And already we're getting something that looks like that. This question looks quite abstract, but when you actually write down what's given, it kind of works out quite nice. So divide everything by 12 and I get my statement there. 4 marks, pretty good. And calculate the area of the shaded region. Okay, so the shaded region is a sector. Do I know the angle? Right, okay. So I don't know the angle, but oh no, I can get the angle. I've got this statement here. All right, okay, cool. So area of sector is r squared times by the angle all over 2. And in this instance, the angle can be expressed as pi take away 2. So that is r squared pi minus 2 all over 2. The radius was 6. And I guess I just type this in on the calculator. Or maybe I could probably leave my answer like this actually. 18 pi take away 36. Let's just work it out on the calculator anyway. 6 squared pi, where's pi? There it is. Minus 2 all over 2. Okay, and then let's just check my answer. So it's roughly 20.55 squared. Just check that my expansion's okay. 18 pi take away 36. Yeah, okay, cool. Hey, that was quick, wasn't it? Nice one. Okay, apologies, I'm back and I'm not wearing Christmas jammies, which means I'm recording this at a different time, and it turns out I've been a fool. I've made a mistake, and that is because this area here is the area of the sector, right? Which in terms of my diagram is this bit here in white. But the question's asking about the shaded area, which is clearly, I've not done that. So to get that shaded area, I don't have to do too much more work, but I just need to realize, okay, it's the area of the entire circle, take away the area of the sector. So the area of the circle is going to be pi r squared, and then I'm taking away the area of the sector, which I've worked out already. So in this question, pi, I think pi was, sorry, no, pi stays the same. The radius is 6, so let's change that. And let's expand the brackets at the same time. So minus and minus is a plus. And solving this, so 36 take away 18 is 18. And then I'm adding 36 on. Okay, so let's get an approximate answer there. 18 pi plus 36 is 92.55. Okay, so let's just do some numerical checks, just make sure that seems okay. So the area of the circle on its own was pi r squared. The entire circle, yeah, it's 113. The sector was 20.5. Yeah, so that's about right, isn't it? Let's just take away 20.55. Yeah, brilliant. Yeah, so that now seems okay. Cool. Okay, question 7. Making good progress here. Well, I don't know, feels like it. It's quarter past 12. I reckon I can get it done by 1 o'clock, guys. What's going on with this question? So it's a composite function question. We're given two functions, f and g. Got that there, and we've got g, which is basically a straight line, and we're plugging in those numbers. Okay. So the first question just says, write down the range of f and the range of g. So let's think. Range of f, we're putting in negative numbers into the equation x squared minus 19, and then we're wondering what comes out. So you can think about this graphically, or you can literally just plug in numbers. I think I'm going to consider the graphical interpretation. So it's an x squared graph, which means it does something like this. The minus 19 tells us that it passes through minus 19 on the axes. And because we're only plugging in negative values, we're only really considering this part of the curve. Well, that's a dodgy drawing, that, isn't it? Blinking heck. So the x values that come in are just the negative ones. The y values that come out are anything above minus 19. Right? So if you plug in 0, you get minus 19. If you plug in a large negative number, anything large and negative, when you square it, becomes positive. So we are going to get as our answer minus 19 to infinity. Curly bracket, because it's a curly bracket for the 0. We're plugging in values approaching 0, but not 0 itself. The other one, so this was F. Let's have a look at G. Oh, bloody hell, that is terrible. Let's just write that again. So G is the function 6 to infinity goes in, and the equation is 1 take away a half x. And once again, we're wondering what comes out. So if you plug 6 into the function, you're going to get 1 take away a half of 6, which is going to work out as 1 take away 3, which is minus 2. And if you plug in a large number, well, you're going to have 1 take away half of a really large number. You can hopefully see that that's not going to be bounded. You're just going to get negative numbers, and they're not going to be bounded. So that is values between minus 2 and minus infinity. I'll put the minus infinity first. There we go. So that is that first bit sorted there. Part B, domain and range of fg. Okay, so fg is, I'm going to substitute the function g into f. I think I need to do that in part C as well. Okay, so the function fg is going to be, do the function g first, then the function f afterwards. So that is, you start with these numbers, you do the function g, and then once you've done that, you do the function f after it, and then you see what you get out. So the domain of fg is just what numbers went in the first place, and that is the same as the domain of g. What numbers come out? So once you do the function g on it, the numbers that we get out are minus infinity to minus 2, and then you're going to do the function f on that. So we already know that plugging in a large negative number into f is going to be unbounded. Plugging in minus 2. Okay, so let's see. So if I plug minus 2 into this function, what would happen? Minus 2 squared minus 19. That's going to work out as 4 take away 19, which is 15. So it's as if we cut the function here. It's 15, and then we work out from that point rather than the lower one. So the numbers that we get out, if we put 6 to infinity into g, then into f, we're going to end up with minus 15 on the lower end, and then unbounded on the upper one. Okay, cool. Write down an expression and then solve that. Okay, so fg, let's see. Okay, so I'm going to plug the function g into the function f. So the function g was 1 take away a half x, I think. Yeah, it was. And then that's going to go into x squared minus 19. So this entire thing here is going to go in place for the x there. Oh, galaxy pen, beautiful. So it's going to look as follows. 1 take away a half x squared, take away 19. That's my expression FG. I could leave it like that. Do I need to expand it? It doesn't say expand it. We'll leave it. It'll do like that. And there's a second part, which is solve the equation. So it's FG equals 2x minus 26. So let's take FG. Let's take this thing here and sub it there. Okay, this probably will end up as a quadratic equation. Let's take it all over to one side. Let's take it all over to the left. I won't expand this just yet. Okay, so the outer bits here are going to work out as 19 from 26 is 7. And let's expand this now. So it's going to be 1 take away 2 lots of the combined term, which is going to be a half times 1, which is just x. There we go. And then times in that bit out, half x times itself is a quarter x squared. Okay, let's tidy this up. A quarter x squared, take away 3x, 1 plus 7 is 8. And I don't like this. Let's times it through by 4. Make it a bit nicer looking. There we go. Okay, and then I can solve this. I can factorize it. We're going to have 4 and 8. So either x is 4 or x is 8. However, there might be a catch here. There's 2 solutions, but I need to look into what numbers I'm allowed to put into FG. And the numbers that were going into FG were 6 to infinity, right? So when we got 2 answers out, we've got either x is 4 or x is 8. We're allowed to put x is 8 in because it's in this range 6 to infinity. Whereas this one, x is 4, that's not in that range. So even though it did solve this quadratic, it's not a solution in this instance. Okay, so since we were dealing with the equation FG, you can only, the only solutions are numbers that can be put in the first place. So if you're only putting numbers in above 6, then yeah, this is no good. Cool, that's that question. Okay, what's going on here? So this is a geometric sequence question. It's talking about sums to infinity. So sum to infinity of a geometric sequence, the first term is a, and the common ratio is r, and that's 10. Okay, and then it says there's a different sum to infinity for a different geometric sequence. The first term is still a, but the ratio is now 2r, and you get 15 from that sum to infinity. So let's just write that down. So the sum to infinity for the first one, the ratio was r, the starting term was a, that was 10. So I'm going to chuck a 10 over here. That was the first thing they told me. And the other one was, if I write the statement again, but I use 2r for the ratio, it's going to work out as 15 instead. So I'll just write that down. Okay, cool. I have to find the value of r. That's what the question's asking me to do. How am I going to do that? I'll take both of these denominators up. I don't like these being down here. Oh, okay, brilliant. So these are both rearranged so that a is the subject of the formula for both. Therefore, I can set these other bits equal to each other. Okay, and then if I expand all this and solve it, I'll be able to get the value of r. Let's take r over to the left so that it's a positive quantity. Let's take the numbers over to the right. So minus 10r plus 30r is over there. 10, 15 take away 10 over here. So it's going to be 20r and 5, and this is going to work out as 5 over 20, which is a quarter. Cool. Nice. And what else am I supposed to do? Find the sum of the first four terms of the first series. Give your answer to 2 decimal places. Okay, so just the first 4 terms. And it's the first sequence, the one with a and ratio r, not 2r. Okay, I think I need to find the value of a to do this, so I'm going to go back to the equations I had, although I know the value of r now. So if I write down the statement that I had to begin with, the sum to infinity was 10, and the ratio was a quarter. Struggling to find the pen. There we go. So I can tidy this up. So 10 times 3/4 is going to give me my starting term, which is 7.5. Okay, so now I've got a sequence. The starting term is 7.5. The ratio is a quarter. I've committed a sin here. I've done the decimals and fractions. Let's call it 15 over 2. There we go. That's better. So the sum of the first 4 terms, there's a formula for this. Okay, so I know the value of a is 15 over 2. I know the value of r, which is a quarter. Struggling to click on the right buttons now. And I can also replace the denominator as well. There we go. This is definitely one for the calculator. I haven't used it for a question or two. Let's go back to it. So the denominator is 1 take away a quarter. The numerator is 15 over 2 times brackets 1 take away, and I'll put this in a bracket just in case, a quarter, and that's raised to the power of 4. Okay, let's see. And that is 9.96. What did I need to do in terms of... Okay, it was 2 decimal places. Okay, cool. So that'll do then. That's lovely. All right, partial fractions next. This tends to be a nice one, although there's quite a cheeky part B here that we're needing to work out. So let's start by writing down the fraction. And we've got x minus 1 squared, x plus 4. So this is going to change too. So we'll have x minus 1 on the bottom, x minus 1 squared, and x plus 4. Just so you know, it doesn't matter which way you order these a, b's, and c's. So if your fraction a has like an x plus 4 on the bottom, it's not a problem, as long as you have 3 fractions with these 3 bottoms. So let's multiply through by x minus 1 squared, x plus 4. And what that's going to do is, initially it's going to cause a lot of mess, but then it will tidy things up quite nicely. Oh, that fraction bar is a little bit on the wonk. Never mind, so let's multiply by this, top and bottom. Actually, let's write it out first, and then I'll include that extra bit. Okay, so let's multiply each term by that. And some parts here are going to cancel. So for the A term, we're going to have one part there cancelling. For the B term, it's going to be this entire bracket, and then for the C term, it's going to be the x plus 4. And on the left side, it's going to be everything there with everything there. So I get the following. In an exam situation, you don't need to write that intermediate step, this thing here, if you don't want to. Just useful to know where it comes from, I suppose. So that's what we are left with. So I'll revert to subbing in numbers now, I suppose. So let's sub in x is, let's go for x is 1 first. Well, that's going to do, the reason why I've chosen this, if I sub it in to these brackets here, this bracket's going to work out as 0, so is this. So I can see already that this statement's only going to involve b once I sub in this number. So A and C term cancel. 8 plus 7 take away 25 is 15, take away 25 is minus 10. So B is minus 10 over 5, which is minus 2. Let's also sub in minus 4, so that we can get everything to cancel except for the C bit. Oops, don't need to write that. C minus 4 take away 1 squared. Okay. This is it's getting late. I'm getting sloppy, so I need to just type this in. It's probably safer. Do I guess it? I don't think I even risk that. Let's just work it out. 75. Okay. Minus 5 squared. That's going to work out as 25. So C is 75 over 25, therefore C is equal to 3. Okay, cool. This is what I've got at the moment. Let me take that statement and I'm going to copy and paste it actually. And I've worked out that C is 3 and B is minus 2. Okay, let's get that in. That's minus 2, that's 3. Okay, so from here, what I could do is I could sub in a different x value, and that would eliminate all of the other variables apart from a. The other thing you can do is you can compare coefficients, right? And I think this is usually a little bit quicker. What you can do is you can say, okay, notice on the left-hand side there's 8x squared currently. If you were to expand all of the right-hand side out, you'd end up with a lot, whatever a is, ax squared from expanding this bit here. And if you expanded this middle bit, you wouldn't get any x squareds there. There would just be x's and numbers. This last bit, you'd get 3x squared from. Right. Then you can say, well, okay, you can ignore the x squared part. And I'll just solve this equation. And you can take the 3 over and you get that a must be 5. Cool. So bit more copying and pasting actually. Let's take that original statement. Oh, I didn't copy and paste where I wanted it to. There we go. So I worked out that A was 5, C was 3, and B was -2. Cool. That's part A. What is part B? Use your result to part A, express this in partial fractions. So notice this bit's bolded. It doesn't want us to go through the entire partial fractions process again. In fact, even if we did do that, they wouldn't give us the marks for it, right? So don't give yourself loads of work to do. This is one of those like tricky parts that once you've seen how to do it, it's suddenly okay. But if you haven't seen it before, it's a little bit of a weird one. Right, so it's 9x squared plus 5x minus 24. Let's just jot that down for part B. 9x squared, forgotten it already, plus 5x minus 24. And I believe the denominators were exactly the same. Yes, they were. Okay, so I've put the result for part A up here. This is what we worked out in part A, and we've got to somehow use this to solve this set of partial fractions. Now, the thing to notice is this fraction here, this part B fraction, it's kind of similar to this one in part A. The denominator is exactly the same. The top, well, there's some slight differences, isn't there? There's we're about an x squared out. The x value's a little bit out. The number's very close, but it's still not quite there. So what we can do is we can say, okay, this fraction here, it's what I had in part A, except it's a little bit more. So let's write down what we had in part A, which was this. So that was what we had in part A. But we've got an extra x squared. We've got 2 less x values. And we had minus 24 instead of minus 25. So that's an extra 1. So that's the numerically, or like algebraically, that's the difference between the two expressions, that bit there. We can write this as follows. Basically just split the fraction up. And this thing here was our part A answer. So if we wanted to convert that into partial fractions, we've already got this. This thing here. So this quadratic, x squared minus 2x plus 1, it can be factorized. I believe it factorizes, yeah, to x minus 1 squared. So if I tidy this up a little bit, they're going to cancel, and it's going to work out as 1 over x plus 4. Okay, so taking what we had for part A as well, essentially what we've got here is the answer to part A, except we've got 1 over x plus 4 extra. So I'll take this answer, but I'm going to have an extra 1 over x plus 4 at the end of it. So part A's answer was this. Let's grab that and pop it here. And then of course these things are relatable, so then we can just say we're going to have a very similar answer to part A, except the coefficient above the x plus 4 fraction, that's going to be a 4 instead of a 3. Okay, question 10, we're getting there. It's more trig. This time we look to be using the compound angle formulas instead. Initially we're solving this equation. Tan x plus 45 is equal to 8 tan x. So I can see there's a useful formula here. So I suppose I'll use that for this first question. Let's just write the formula down initially. Tan of x plus 45 is 8 tan x. Okay, so if I use the tan A plus B formula, it's going to be tan of x plus tan of 45 divided by 1 take away tan x tan 45. Right hand side stays as it is. Now, something convenient, you might already know the value of tan 45. It's a good one. Just 1. So therefore, you can replace these with 1s, which makes it look a little bit more manageable. Tan x times 1 is just tan x, so I'll just leave it like that. Okay, so let's take the denominator up. And what it might have been a good idea to do actually is I'll call it t, just because it looked a bit confusing there. So it's going to be t plus 1 over 1 minus t. And let's take that up. Let's expand the bracket. And let's take it all over to the left side to get 8t squared. Actually, let's just write it down bit by bit. 8t squared minus 7t plus 1 equals 0. Does that factorize? So 99% of the time these do factorize. No, I don't think it does. Okay, so at this point, it could be that I've done something wrong. But something is telling me that I think I've done everything okay. So I'll just double check. But what we might have to do is we might just go with it and we'll solve it using the quadratic formula and pretend none of this happened. Let's just check this. So that's gone up. Yeah, no, I think I'm happy with it. So it doesn't have to factorize. That you do encounter questions where it does happen. I'd say 95% of the time it does factorize. So you'll have like that very occasional like 5% situation where you'll use the quadratic formula on it. Let's get our calculator back out then. I haven't used it for a little while. So it's going to be a polynomial, degree 2, and it's 8 minus 7 and 1. Yeah, okay, so it's not nice answers. So the t values are approximately 0.695, and the other one is 0.17, let's call it 180. Okay, and we'll just include our workings here just to get in the habit. There's 49 take away 32, which is 17. Okay. Right, so apparently tan is either 0.695 or it's equal to 0.180. So the x values are just the inverse tans of those. Let's see what they work out as. (34.8 degrees). And 10.2 degrees. The tan graph normally repeats itself every 180 degrees. So there would be another answer, for example, at 190.2 and 214.8. But I think in the question it said from 0 to 180. So I think I've got all the answers I need to there. Yeah, brilliant. Let's have a look at this next one then. So this is a harmonic one. We've got 13 sine theta take away 6 cos theta. So let's write that down first of all. Root 13 sine theta take away 6 cos theta, and we're trying to express it as r sine of theta minus alpha. Okay, so what we'll do first of all is we'll use the compound angle on that. So the r is going to keep out as a factor. Let's just check the compound angle formula. It's sine a cos b minus sine b cos a. So that is going to be sine theta cos alpha take away sine alpha cos theta. Okay. So let's expand these brackets. Just multiply r back in, essentially. And what I'm going to do is I'm just going to write this particular expression here. I'm just going to put the cos a in front of the sine theta. We'll see why in a moment. Okay, so since this is an equation, the two sides need to have the same amount. Specifically, I've got sine theta over here, and I've got sine theta over there, and I've got a root 13 in front of it, and I've got an r cos a in front of it here. What that tells me is these bits here, they must be equal to each other. And from a similar argument, I can do exactly the same for what precedes the 6 cos thetas. Technically there's a minus here, but because there's a minus there, I can ignore it. I can say, okay, there's a 6 there, and an r sine a there, and I've got two equations. Cool. Now, I think the way you guys did it in class was geometric, like you drew a triangle, and I think that's probably what I should do as well. Yeah, let's not mess around with it. Let's just draw a triangle. So the triangle has got, it's a right angle triangle. The hypotenuse is r, the angle is a. So if you do a bit of trig on this, I won't do this right now, but the opposite should work out as r sine a, which in this case is 6, and the adjacent should work out as r cos a down there, which is root 13. So to get the value of r, we're going to use Pythagoras. So we're going to do root 13 squared plus 6 squared. And this looks promising. There we go, that looks right. It's a bit weird that they had a root 13 at the start, so I was hoping that it would kind of work out okay in the end. In terms of the angle, we're going to use trig. Specifically, we're going to use inverse tan. So we know the opposite and we know the adjacent. So it's going to be inverse tan of 6 over root 13. And that's one for the calculator. Got our inverse tan already. 6 over root 13. Let's call that 59 degrees. It's very close to that. There we go. So we've got r is 7 and a is 59 degrees. So therefore, the original statement, this thing here, that can be expressed as 7 sine of theta take away 59. Cool. So that's the first bit of B done. What else do I need to do for it? I need to solve the equation that equals -4. Okay. Right, okay, so the thing to notice is obviously we just had this. We've worked out that it's equivalent to this, so we can change them. And that is the first thing to do. I don't know why I've changed pen color. Just thought I'd jazz it up, you know, it would look nice. I'll take the 7 down. And now I've got a trig equation. I don't really like the argument being different here, so what I might do is might say something like let x equals theta minus 59. So now I have this instead. Easier to deal with. So let's solve this. So we've got our sine graph again. Let's just do it very rough this time. Hey. So inverse sine of -4/7 is minus 34.8 degrees. It's a bit low actually. Let's pop it there. Minus 34.8. We're going to have another value over here by doing 180 minus it. 214.8. And we're going to get the last value by doing the original point minus 34.8, add 360. 325.2. Okay, so these are x values. So remember we've changed the original expression, haven't we? This isn't theta, so we should probably change it back. So it's theta minus 59. I'm feeling lazy, so we're going to do all these in one go. So to get the theta values, what we're going to do is we're going to add 59 onto each of these. Okay, so it's just taking it over the other side of the equation essentially, but just doing it all 3 times. So minus 34.8, 59, that is 24.2. The next one is 273.8, and the last one is 384.2. And I was trying to find values between theta is 0 and 360, and that's out of the range. So something to keep in mind for this question is we're aiming to get angles between 0 and 360. Notice that we ended up including this. So even though this originally was outside of the range, minus 34, when we did the transformation on it, when we added the 59 back on, it became in the range. So it's worth including answers that you think, oh, that is a bit outside the range, just in case it sort of fits back in after you've done a transformation like that. All right, we have pretty much made it. Last question. It's 3 minutes before 1 o'clock. So let's just get this one out of the way, shall we? So it's an inverse function problem. The way to proceed would be write the equation as y equals, and from here try and make x the subject of the formula. So make x the subject. So because there's a statement involving e, I will eventually need to take a logarithm, but I want to make sure that the e is on its own in the equation. So let's take the 8 over first. There we go. And now I can go ahead and use logarithms. Here's the rule for logarithms if you're not sure. So if you have e to the power of something equals b, it can be expressed as a equals ln of b. So in this instance, I'm going to have ln y take away 8, 4 take away x over 3. Bit more rearranging. I think I might even take this entire expression over and then take the log back, just so that it's positive. Yeah, I think that's what we'll do. And then I'll take the 3 up, and then we should be done. You can leave it like that if you want to. I will times through by 3. There we go, cool. So this is my inverse function. 12 take away 3 log, and I'll just change the variables back. There we go, there it is. What else is there to do? Write down the inverse domain. Okay, so the inverse domain then is the same set as the range of the original function. So if I find the original's range, then I'll have done what I need to do. So So the original function is e to the 4 take away x over 3 plus 8. Yeah, plus 8. And the numbers that are going into this function are minus infinity to 12. And what I'm concerned about is what comes out. So let's think. I'll plug 12 in just to see what's going to happen. I think I've got a bit of an inkling. Yeah, so the power here, 12 over 3, that's 4. So the power is going to work out as 0 in this instance. E to the power of 0 is 1. It's going to work out as 9. So when I plug 12 in, I get 9 out. If I plug in a large negative number, see what's going to happen. We've got a double negative here. It's going to work out as a positive. And what I know about the exponential function is it just goes off on one. It just accelerates and diverges rapidly. So this isn't going to be bounded. This has no upper limit. So putting those bits together then, the range of the original function is 9 to infinity, and therefore as an extension that is also the domain of the inverse function. That's the paper. Whew, what a fun time. Okay, one more small correction as well. This one's not too tragic, but I've copied the domain brackets down wrong. The brackets are both curly right now. It was minus infinity to 12, but in the question, the 12 had a square bracket indicating I'm allowed to plug 12 in. It almost looks square, but it's not quite, so definitely need to emphasize that a little bit. So I'm allowed to plug 12 in, which means I'm allowed to get exactly 9 out. So this bracket is going to change here. And there's my slightly improved answer. Okay, thanks for watching, folks. Hopefully you found it useful. If there are any queries or if I've done something wrong, that's always possible, isn't it? Do let me know. Just pop me a message and I can go through it. Alternatively, if it's just something that you need a hand with, then I'm happy to go through that as well. Enjoy the rest of your holidays and catch up with you soon. Take care, everybody.